My iPad glitches a little bit, so I've got to break up the videos. So it's literally, this is just a continuation of what we were talking about. If we want to know how far something's going, the overall length of the path, we're not worried about direction. That's a scalar quantity that we call distance, and the short form for that is letter D. If we're more curious about where we are relative to where we started, then we call that displacement. It's a vector because we need to know the direction we are away from our starting point. We call that one displacement, and it's D with a little vector hat. Similarly, we can talk about how fast something's moving in two ways. The one that your car measures, we call it speed. It's a scalar. Nowadays, we've got cars with compasses built in, so we're going to ignore that. Speed is just keeping track of how quickly you're covering the ground. How quickly are you moving along that path that you're traveling? Speed is a scalar, and we literally just take the distance number and divide it by the time number. That tells us our scalar speed. That's what your speedometer would measure. If we go one step farther, there is a vector for how fast. It's called velocity, where speed was the distance divided by time, the scalar distance divided by time. Velocity is the vector displacement divided by time. When we start using equations, the short form for velocity equation is v with a vector hat. I'm going to draw it as an arrow. It could be typed as a bold or with just a single bar. Its displacement, which we said was d with a vector hat, divided by time. In physics, unfortunately there's different notations, but a common notation is to write time with a little delta triangle in front, just to remind us that it's the change in time, how many seconds it took for that displacement to happen. And the scalar equation is kind of the twin to that. It's distance, which is this plain old letter d, divided by time. Again, we're going to use the delta time, and the short form to make it match, we're just going to call it v. So v equals d over t. If it's got vector hats, that's our vector equation. That's velocity is displacement over time. But if we're not concerned about direction, if we're just like talking about our car and how fast we've gone in our car, then it's our distance number divided by time, and we're going to call that speed. That's a scalar. It does lead to some weird things. Let's say at the start of class, I start by standing at the door saying good morning to you as you come into class. Then over the course of the class, I walk back and forth by the whiteboard a bunch of times. Maybe I walk down the aisles of the classroom a bunch of times, zigzag around. And then at the end of class, I come and I stand at the door to say goodbye to you. In that weird case, my distance would be some sort of number. Maybe if I'm wearing my watch, I could tell you how many steps I took over the course of a class. But my displacement value, if I start and end at the same spot, that's a displacement of 0. Technically, if I didn't know any better, I haven't changed position over the course of that period. I ended up exactly where I started. If I pushed it from the distance, I could find my average speed of walking around. I'd have to take that distance number and divide by however many seconds I was walking for. But when I find the average velocity, when I take my displacement number, the displacement number in this weird case is a 0. So I'd end up that overall I've got an average velocity of 0 if I ended up back where I started. So the bottom line is how far and how fast. Since there's scalars and vectors, since there's two kinds of quantities, there's two ways to look at how far and how fast. The one that we kind of use in our everyday life is the scalar, the distance, and the speed. But where we're going to sort of push as we go more into physics, and we'll need it as we do more complicated applications, is we'll have to use the vector version where direction is important, and we'll call that displacement and velocity. I think that's enough to get us started. We're going to jump back to, well, I'm going to get you to do a little homework problem on this, then we're going to jump back to relative motion.